Okay, today we're going to make a start on chapter 10, which is about random vibration. We're going to talk a little bit about an introduction to what it's all about. Then we're going to discuss some of the sort of basic statistics involved in random vibration. Okay, talk about these sort of processes and how the statistics help, and then we'll talk a little bit more in detail about some of the theory behind it. Correlation functions and spectral density, that's all going to be, that's sort of the theory behind it, and I may skip over that because in a sense you don't really need to know the derivation, but you do need to know how we then apply the stuff later on. Okay, so we'll see how we get on. The maths in these two bits is a little bit tough, but interesting in this bit is where we see Fourier transforms come into use, because power spectral density is a frequency spectrum. Okay, so let's make a start. Up to now we've been dealing with deterministic vibrations. Okay, and deterministic is a term that we use to represent the fact that we know displacement, velocity and acceleration certainly. Okay, so we've been working out things and we come up with a particular value for acceleration or displacement. Okay, we found functions for x of time, x of x, which is a function of time, and that x is the displacement. You can plug in a value for time and you'll get a number as your answer, which is the displacement. Great, we know that's fine. Often, though, is that you cannot precisely determine those things, okay? And that means we're dealing with non-deterministic vibration, and the other term for that is also called random vibration, okay? So you're measuring something, okay, and that motion might have a random element to it that you can't control, and so you don't get the same response every single time, okay? And that response will therefore be a random vibration in addition to what you're trying to measure. So the details of the process can be known, but the statistical information, the details of the process are unknown, but the statistical information about it can be determined. Okay. Now an example of this is a road surface. Okay, we don't know the actual profile of the road surface to put into our suspension system of our car when we're developing the vehicle or whatever, but we know we can represent the road surface, the bumpy, random nature of the road surface, as some statistical information that we can therefore feed into our system. And what we're going to do today is we're going to look at, you get a piece of information about the road surface, that's a piece of statistical information, you feed that into your system and you'll get some sort of feel of how the system is going to respond. And then you can obviously tune your damper and your spring and all that sort of stuff to do with your car, based upon that answer. Okay, so that's what we're going to look at today, and that's the sort of the final goal of where we're going to be heading, such that you could take some statistical information and then look at what the response is going to be based upon that. And again, you're not going to get a deterministic response. Okay, you're not going to say, okay, well, it's going to move by this much, obviously, because you've got a random input being put in, but we're going to get a feel of what the response is going to be like. So before we can dive into all the stuff at the bottom, we need to understand some basics of the sort of probability theory and statistics. Okay. Now, let's say we've got a random variable x. Okay, so it's x. As time varies, x moves up and down. Okay, it's random. And we've taken n. We sampled it. We've taken n experimental values of that value. Okay. And the probability that a chosen value of x is smaller than a certain value, here I've called it x with a little squiggle underneath, that's a certain value. So let's say I'm measuring something, and it's I'm getting measurements between, say, 0 and 5. Okay, and I want to work out whether the probability of what I'm measuring is going to be greater than or equal to 3. Okay, so, less than or equal to 3. And so this value here would be 3, okay, and x is going to be some number between 0 and 5. Okay, some of those n values will be greater than 3, some of them will be less than 3. I want to work out the probability. Well, you can work it out. You can write prob then you have square brackets, x is less than or equal to x with a squiggle. So it's basically the number of samples, okay, where of that, with the number of samples that are less than 3 over the total number of samples, and that makes sense, okay? Let's assume we've got a square distribution, okay, so there's an equal chance whether it's going to equal 1 or 4 or whatever, okay? Let's assume I take 100 samples, and 60% of them are less than or equal to 3, okay? I have, so I have 60 samples that are, my n with a squiggle underneath is 60, divided by 100 I get 60%, okay? 0.6, that's essentially what's going on. So the probability is going to come out as a percentage or a fraction. And as n approaches infinity, you get this thing called the probability distribution function, okay? And that's represented by a capital P, okay? Which is a function that gives you the shape of, or essentially how it's going to be distributed. Now, what we're really interested in is this thing called the probability density function. Okay, it's also known as the PDF, and you may come across this in other areas of engineering. PDF, probability density function, and that is denoted by little px. Okay. And if you take the derivative of px with respect to x, it's known as the PDF. Okay, so therefore, and the total area underneath the curve of a probability density function is always going to be 1. Okay, because the idea is that it represents the chance that you're going to get a value within that, underneath that curve. Obviously, the idea is that that curve will represent any value you get. So obviously, the chance you get a value underneath the curve is 1. But obviously, you can separate the curve into smaller chunks. And then you can work out what the chances are that you're going to fit in a certain area of that curve. So that's, obviously I said that the derivative of px with respect to x is known as the PDF. So obviously the integral of the PDF gives us that probability distribution function. Okay. And like I said, the area underneath that curve, okay, between minus infinity and infinity is always 1, because you've got a chance of 100% that your value is going to fall underneath that curve. That's the whole idea. This curve could be a variety of different shapes. Okay, I talked about a square shape just a moment ago. You could have a normal distribution, which we're going to talk about, all sorts of things. Basically, the idea is that you're going to have a 100% chance that your value is going to be under that. But obviously, if you change the limits between, say, A and B, okay, then you can work out your probability that your x is going to land within that curve between A and B by using this equation. I'll show you that in a minute. So, for example, we've taken some values here. I can't remember the exact example that I used, but I talked about it. Take a random signal of 256,000 points and then measured in volts, for example. Okay. The histogram, okay, displays, we've got the value of the sample down here and how many times that's occurred. And obviously, if you add up each of these little things here, okay, so obviously at 120 I've got about 520,000, 5,200 or whatever. You add up all of those, you're going to get 256,000, okay? And that's how those things are distributed, and that's called a histogram, okay? There's a little bar for each of these values, okay, and that will show you how many times that's occurred. Now the PDF of this, the probability density function, also looks like a normal distribution. And so the chance, and you can see that this is asymptotically going towards 0 and, I don't know, 100 or 200 or whatever, okay? And, but the chance of my value, so I pick a value, occurring in here, is going to be given by the area under that curve, okay? Now the area under that curve is 1, as it happens. But say I wanted to determine the probability that my value is between 120 and 130, okay, then I can use them as my limits, okay, 120, 130, and I get an area here, and that is obviously going to be a not 100% of this, okay. So you can plug in your limits here, and you get a value, and that value will be the chance that it occurs between there. Now this is important in terms of, say, manufacturing processes. You've got a machine that's producing lots of widgets, and your widget needs to have a certain dimension that's within a certain, you've got a tolerance on that thing. And some of the widgets that come out are outside that tolerance and some of them within. And you want to work out, well, how efficient is this machine? Do I need to replace it, perhaps? And so you can look at your limits, the tolerances of that widget, the dimension, okay, and you can look at the distribution of the parts that are coming out, and you can do this. This is the response of the machine. The chances are the widget's going to be somewhere in there, okay, but we want to make sure that our widgets are between these two values. And so you take the limits, you do the integral, and you'll get a percentage. And obviously if the machine's producing widgets 95% of the time that are fine, you're just tossing 5% of them, then obviously that's probably okay. But if your machine's producing, say, 40% are within tolerance, the rest are junk, then obviously you might want to think about replacing your machine. So that's PDF, okay? Essentially the area under this curve is always going to be 1. And when we're trying to work out the probability, which is going to be a percentage or a fraction, you apply the equation here, okay? And you set your limits to be what those limits are, and that will give you a value that's less than 1, okay? And that value will be a percentage of, the chances are that something's going to fit in there. So let's talk about some of the actual statistics behind it. We talked a bit about this last week with sort of discrete values. Now we're talking about sort of continuous values. So the mean, okay, f of x denotes some function of a random variable. Okay, we'll talk about the actual random variables in a second. Okay, but the mean, which is denoted by mu, f is because we're talking about a function, can also be written as e open square brackets f of x. Okay, and e stands for expected value. Okay, if we have a process and it's got a mean value, like I said, the things coming out vary. Okay, but we can expect the thing to have a certain value, and that expected value is known as the mean. Okay, and you can also write it as f of x with a bar across the top. Okay, and that is denoted by the integral of f of x times by px, which is our PDF, dx, okay? So that gives us the mean value. Now, what we can actually do, if f of x is x, okay, so we're just not worried too much about the function, then look at this equation, I've called it equation 1, but that's wrong, okay, gives the expected value, also known as the mean value of x. So mu x, or e of x, or x bar, is the integral of x px dx. Okay, so that gives us the mean value of x, which is our random number. And similarly, if our function is x squared, we get the mean square value of x. Okay, we'll talk about these things in a moment. Mean square value. So obviously you stick in x squared into there, into that function, and then you get this term. Okay, and that's the expected value of x squared. And then we can come across this term called root mean square, which you've probably heard before. Okay, and that is a term that describes the, I've got it in here somewhere. It's a statistical measure of the magnitude of the varying quantity. Okay, so this root mean square, so it's this term. Yes, this is the square root of this term. Okay, because it's the square root of the mean square. Okay, this is what the mean square is. And you take the square root of it, you get the root mean square. And like I said, it's a statistical measure of how of the magnitude of the varying quantity. And we'll come across this later on. We talked a little bit about variance last week and standard deviation. Well, okay, that can still apply here. Okay, the variance is how far your things vary from the mean. Okay, and so we've got, last week we had the sum in here, but here we've got an integral because we're dealing with a continuous thing. Okay, there's your values that vary. Okay, there's your mean. You take one from the other and square it. Okay, and then you stick it into that integral and you get the variance. Now you take the square root of the variance, you get your standard deviation. Okay, so if we went through the process and multiply this out, okay, you get x squared minus 2x bar x plus x bar squared. Okay. And obviously you can separate this out. This is now 3 integrals. So you've got this one, x squared px. Well, that we've seen before. That's our mean square. This one here. Okay. This one over here is our basically what's that one? That's the mean squared. Okay, times by 1. Okay. So that's the mean square, and this is the mean squared. And then here we've got 2x bar x. Okay, because this bit, that's a constant, so that can come out. That bit we've seen before, and that's just the mean, x bar. So you get 2x bar times x bar. Okay, and obviously 2x bar squared minus x bar squared gives us minus 1x bar. And so you end up with this. So you get the mean square minus the mean squared gives us our variance. Okay, the mean square, so this is x2 underneath the bar is the mean square, and this is the mean squared. Okay, one minus the other gives us our variance. And you take the square root of that and you get your standard deviation. And those two things, the mean and standard deviation, are the things that give you information about your process and about your random variable. Okay, if you've got you can have a mean of 0, and your standard deviation will give you how much that value, how far it moves away from 0, and that distribution will give you the PDF and all that sort of stuff. Now we covered the root mean square thing. Okay, that's the square root of the mean square. Well, if our mean is 0, then this term is 0. So the square root of that is our root mean square. Okay, so the square root of the variance is the root mean square if your mean is 0. Okay. So that's, which is what I just said. So let's do an example. Okay. Due to a manufacturing error, the rotor eccentricity, okay, we're making a rotor, is found to have the following distribution, or PDF, okay, where we've got P of x is kx squared from 0 to 5 millimeters, and 0 elsewhere. Okay, so that we've got some function, which is a function of x squared. K we're going to determine, it's some constant, okay, and between 0 and 5 millimeters, we've got a probability that it's going to that my values are going to be somewhere in there. The eccentricity is going to be between 0 and 5. Okay. And it says find A, the mean standard deviation and the mean square value of the eccentricity, and B, the probability of realizing x is less than or equal to 2. Okay, so I've got my function, my PDF, it's going to be some shape. Let's see if I can draw a shape. Let's see how out of sync. Oh, that's not too bad. So it's some kx squared. So if this is x, this is P of x. Okay, it's going to look something like that, isn't it? Okay, we'll see. Okay, obviously coming up from 0. And this is between 0 and 5. Okay, 0. So there's 100% chance that my widget my eccentricity is going to be in this area, okay? Because we know that the integral of minus infinity to infinity of px is 1. Okay, there's 100% chance. And this second part of the question, B, is we're saying, okay, well, let's say x is, let's take the bit here of 2. Okay, what's the chance that it lies in this bit here? Okay, and we're going to work that out. So let's go through the process. First off, we need to find the mean, and we need to find the mean. Clear ink. Close it. This is really annoying. So first off, we need to find the mean, the standard deviation, and the mean square value of the eccentricity. So to find the mean, we use our equation. Sorry, before we can do that, we need to find k. And so we're going to work it out. We know that, like I said, this function equals 1, because we've got a 100% chance that our eccentricity is between 0 and 5 millimeters. Okay? And so we plug in our function, kx squared, okay, dx, you take the integral of that between 0 and 5, you know that equals 1. Well, the integral of x squared is x cubed divided by 3, okay, multiplied by k, which is a constant between 0 and 5. You stick in 0 in here, you're going to get 0. You stick in 5 in there, 5 times 5 is 25, 5 times 5 is 125. And so you get k times 125 divided over 3 equals 1, therefore k must be 3 divided by 125. Okay, so that's just working out what k is. And we need that for the next step. The mean is xpx. Okay? Well, k we know is 3 divided by 125. Okay? And the integral of x cubed is x to the power of 4 over 4. Okay? Between 0 and 5, you plug in the numbers and you get 3.75 millimeters. So the mean of our distribution, okay, if you remember we had our distribution, looked a bit like this. Okay, the mean, well, this is 5, 0, the mean is around somewhere around here. Okay, 3.75. That's the mean. Okay. So that's the mean. The standard deviation, okay, well we know that the variance is the mean squared minus the mean squared. Okay, the mean squared minus the mean squared. So the mean square we know is x squared px, and we know what that value is. You just square it, okay, it's down here, look. So you work out the process here. Obviously you get x squared times by a kx squared, that's x to the power 4. The integral of x to the power 4 is x to the 5 over 5. Okay, between 0 and 5 times by k, so you plug in 5 to the power of 5 is 3.125. Times by k, you get a value down here. You square root that, and you get your standard deviation, so 0.9682 millimeters. Great, you think, okay, well, what's the mean square? Well, we'd work that out. Okay, that was this term here. Okay, which comes out to be 15 millimeters squared. And the probability that x is less than or equal to 2, well, you apply this function, like I said, between 0 and 2, because they're your limits now. Okay, we know what k is, we work that out. Between 0 and 2 of x squared, where x squared becomes x cubed upon 3. Between 0 and 2, you stick in your k, you get 8 over 125. So I've got a 6.4% chance that my eccentricities can be less than 2 millimeters. Okay? So that's an example of those equations in those terms. Gaussian process or normal process. This is probably the most commonly used distribution for modelling physical random processes. Okay? And it's used all over the place. It's used all over nature as well. For example, everybody's height. If you took a large number of people, the population, and you measure their height, their distribution would be a normal curve. Okay? And it's because, that's just the way nature works. You can't do the same thing for weight because obviously your lifestyle affects how much you weigh. But height is something intrinsic to you. And as it happens, if you took a large population, you get a normal distribution of height. And the PDF for that is given by an equation here. Okay, don't worry too much about having to remember this, but that's the equation. Where x bar and the standard deviation denote the mean and standard deviation of x. Okay, so you took, let's assume height was my x. Okay, I'd have a certain mean height. In this room, the mean height would be 5 foot something, okay, or 6 foot perhaps, if you're all tall. And the standard deviation would denote how much that varies, okay? And you could plot it and then you'd get a standard deviation, a PDF that looks like a normal curve. That normal curve is also called a bell curve because it looks like a bell, okay? And there's a plot of it, okay, for a certain mean, well, mean, in this case, a mean of 0. And depending on your sigma x, it'll either be higher and narrower, or if the sigma x is large, then obviously it'll be lower and wider. And so in this curve, in this particular example, I can't remember what I put in for sigma, but basically the area under this curve will be 1. Okay, and the same for either of these curves. But obviously, depending on your sigma, it changes the sort of the width and the height of it. But the area is always going to be 1. Interesting characteristic about bell curves is that as these bits here drop towards, they drop towards 0 quite rapidly. So often you'll find a lot of people between these. I think this, in fact, in this example, my standard deviation is 1. You'll find a lot of people within 1 standard deviation of the mean. Okay, and then obviously between 2 standard deviations you get more. Between 3 standard deviations you get more, and so on. Okay, and so I've got a value c, positive number. Okay, and this is working out the probability that that your value x here is between a certain number of standard deviations from the mean. Okay, so if c is 1, x is going to be between 1 and minus 1 standard deviations away. Okay, so it's between here and here. Okay, and if x is 2, you can obviously do the same thing, and x is 3. So there's the equation. You plug in the numbers in, and you get a little table here. So within 1 standard deviation of the mean, 68% of your things are going to be within that standard deviation. Okay, within 2 standard deviations of the mean, 95% of your values will be within that curve. Okay, within that area. So 1, that's 65%, that's 2 is 95%, 3 you're up to 99.73%, and 4 standard deviations means you're almost at 100%. Okay? Now this 2 thing, have you heard of 95th percentile? Yeah, have you heard of that? Okay, 95th percentile means that you're within 95% of the, let's assume height, okay? You're within that percentile, okay? You're within 2 standard deviations of the mean height.